Think about what we've been doing. We've taken all sorts of functions, whether polynomial or rational or trig, and we've been finding the derivatives of those functions. And we've looked at applications of some of those derivatives and so on. Well, chapter 4 starts the concept of, what if we started with the derivative and tried to find the original function? So if you look at this example, if we know the derivative of a function is 3x squared, how could we figure out what the original function is? And so you think about it and work your way backwards and you go, well, I think the original function is x cubed, because if I took the derivative of x cubed, I'm going to get 3x squared. And so we start seeing this concept of antiderivative, which is basically saying we're starting with the derivative and finding the original function. And you might notice the definition of an antiderivative. It says a function f is an antiderivative of f, not the. Why is that? And the reason is because we could have all sorts of functions that have 3x squared as their derivative. Here's 3 of them right here. If you think about it, what's the difference? Well, the first one has no constant added to it, or a constant of 0, if you will. The second one has a constant of -5, and the third one has a constant of 97. Now, we know that when we take the derivative of each of those functions, those constants are going to drop out, and we're just going to end up with 3x squared. But this is making the point that we've got an infinite number of functions that have a derivative of 3x squared. And we notate this by saying, well, here's the antiderivative plus some constant. That constant is what's represented up there in those examples of 0, -5, and 97. And so we notate a family of functions with the same derivative by just adding that capital C, which, as I've highlighted there, is the constant of integration. In other words, that's the only difference in all of those different functions, some constant. So we're being told in the notes here that a differential equation has x, y, and derivatives of y. And they give us a couple of examples there. And then they say, well, okay, if we have a general solution that we want of this differential equation, that the derivative is 2. Well, we know that the function itself is going to have to be 2x, because when I take the derivative of 2x, I'm just going to get 2. But it's not just 2x, it's 2x plus some constant. And if you look at the lines over there, they're all parallel. Because why? They all have the same slope, 2. The difference is some constant. In other words, in this case with a straight line, where the y-intercept is. So some of those differential equations are going to be in the form dy dx equals some function. And it's going to be convenient a lot of the times to just say dy equals f of x dx. We just multiplied both sides by dx. And this process that we're going to be going through is called antidifferentiation or indefinite integration. And notice it has a special sign, that integral sign. And so we've got the integral of f of x dx showing there in that example. So they're throwing a lot of terms at us here. Antiderivative, indefinite integral, they mean the same thing. You're going to see both of those used a lot. Make sure you notice the notation here, that's going to translate into this sort of thing. Those are identical, and they're also identical with just plain old y. So we're finding a y value by taking the antiderivative of some function. Okay, and it's important to notice that derivatives and integrals are basically inverse operations. If we found the derivative of some function and then took its antiderivative, we should end up with the original function. Here's a bunch of integration rules. They match up with the differentiation formulas that we've already learned. For instance, look at the first one there. The derivative of some constant over here is 0. So if we take that same thing and turn around and say, okay, if we've got 0 dx, that's just going to be some constant. There's no x involved in it. Look at the next one over here on the left. We've got the derivative of some constant times x. Well, we know that that's just a constant. So if that was take the derivative of 9x, we know we'd get 9. Over here on the right-hand side, if you're trying to integrate just a constant, you know that the antiderivative is going to be that constant times x. And you can work your way through here. You can see that you can pull out constants that if you've got, look at this addition rule right here. How did we get the derivative? Well, it was the derivative of the first function plus the derivative of the second function. So if we're trying to integrate functions over here on the right that are added together, we can split those apart and treat them separately. You'll get used to these rules. Here's a really good one, the power rule. When you start off integrating something that is to a power, like right here, look what you do. You take the exponent, add 1 to it, and then divide by that new exponent. And in all of these, you're going to have a constant sitting out there. And the box down at the bottom reminds us that we can split these apart. We can move constants around. The power rule works backwards. But for right now, we're not worried about the product rule or the quotient rule. You'll get to those later. And we can't forget our trig functions. Our differentiation rules are over here on the left. And take each one of those and compare it to what we have on the right. Notice if I start with cosine x inside my integral, you got to keep in mind that's the derivative of something. Well, what's that derivative of? Well, sine x. And so we've got sine x plus some constant as the antiderivative. Look at the next one though. I've got sine x dx on the inside of my integral. Sine x is not the derivative of cosine x. Negative sine x is. So really, either on paper or in your head, what you're going to have to do is say, okay, I'm going to pull out a negative here, but that means I can put a negative in here. And now then, this sine x is the derivative of cosine x. And so what I've got here is just going to turn into cosine x, but that negative has to come out here. So that's why it's written the way it is. We can't just drop the negative. And you're going to see the same thing happening down here. Look at cotangent. When we differentiate it, we get a negative cosecant squared. That negative pops up here for the same reason it did in the sine x example. Same way with cosecant. I'm getting this for my derivative. If I started with that though, where's the minus sign? You've got to keep it someplace, and so we put it out here when we get our antiderivative. That's easy to trip up on. Okay, let's try a few of these. First one, I've got inside the integral x dx. I'm just writing it like this to remind you that x has an exponent of 1. So I can use the power rule. I add 1 to the exponent, I get x squared, and then I divide by the new exponent, and then plus my constant of integration. If I want to, I can rewrite it like this. Either one of those answers is fine. Looking at b, let's rewrite that, just to remind you that if you get it in this form, it's a lot easier to see the power rule. So I add 1 to the exponent, I divide by the new exponent, and put my constant of integration out there. I'm going to clean that up just a little bit. Keep change flip, and that's probably a better form to write it in right there. C, another example where I would probably rewrite it just to keep straight in my head about the power rule. So I do what? I add 1 to the exponent and then divide by the new exponent. Now this one could trick you if you just go, okay, I got a 3, I'm going to add 1, that's a 4. No, you're adding 1 to a negative 3 exponent there. So I can simplify that a little bit. I don't want to leave the negative exponent there, though, for my x, so I'd probably rewrite it like this and call it done. And again, remember, there's an infinite number of functions that have the derivative 1 over x cubed. Looking at D, I need to remember there's 2 things in that integral. They're being added together, so I can split them apart and treat that as 2 separate integrals. In other words, like this. Now the 2 in the first one is a constant that I can pull out, leaving me just dx there. Now you got to remember what's really there is a 1. So on that first integral, what function would give me 1 when I got the derivative of it? Well, just x. That's for the first one. On the second one, notice sine x is not the derivative of cosine x. Negative sine x is. So if I put a negative sign there, I'm good. But I can't just stick a negative sign in there. So I've got to put 1 on the outside to cancel it out, because otherwise I would have changed the problem. So now on the inside I've got this, which is the derivative of cosine. So watch what happens on the next line. For the first part there, that 1 translates to an x when I get the antiderivative. And on the second one, the stuff I've got in red parentheses translates to cosine x, but the negative sign stays out front. Watch out. That kind of thing is real easy to trip up on. Like the sign says, these can get trickier, and here's 3 examples of trickier. That first thing in A looks like a quotient to me, but the notes have told us, well, we don't know enough yet to do quotient rule kind of things. So that means we've got to translate this into something that's not a quotient. All right, so I can rewrite it. I split my numerators, my numerator, putting each part over the same denominator. I can always do that. And then I'm looking at the first part there. That still looks like a quotient, so I'm going to rewrite it a little bit. Now the second term inside the integral is pretty easy to rewrite as a power to the negative 1/2 power. That first one, though, I've got x to the first power divided by x to the 1/2 power. Since the bases, x that is, are the same, I can just subtract exponents. Now I've got something that's not quotients. And since they are being added together, I can split them apart into separate integrals. All right, so for the first one, I add 1 to the exponent and get 3/2. I divide by the new exponent. For the second one, I add 1 to that negative 1/2 and I get positive 1/2. I divide by the new exponent, and then there's my constant of integration. Probably wouldn't want to leave it like that, so I rewrite it like this. One more time, if I took that last line and I found the derivative of it, I would end up with what I started with. It'd take a little algebra to do it, but that's what I would end up with if I had everything over the same denominator. You might want to try that. Look at B. B is tricky. Looks like a quotient, but we can't treat it as one yet. So you got to look for relationships. I'm seeing sine and cosine. The cosine's squared, the sine's not. So just from having done this a little bit, I'm looking at the sign as though it were part of the derivative of cosine. I know it has to be a negative sign, but at least I'm getting a cloudy mess a little less cloudy. So I can rewrite this maybe in this way. And you look at that and you go, well, wait a minute, the cosine x is to the negative 2 power. Yeah, that means you got to start thinking chain rule backwards.
Oh, no.
So what's wrong with this picture so far? The sine x needs to be negative sine x, right, to be the derivative. So I need to start thinking in terms of u maybe. So if I rewrite this, I want there to be a negative sine x. That means I have to put a negative sign out front to cancel the negative sign in the middle so that I haven't changed the problem. So here's how I'm visualizing it. The cosine x is u, which is being raised to the negative 2 power. The derivative of that is negative sine x dx. These are going to take some practice. All right, if I continue with that thought, then really this is in the form negative u to the negative 2 power du. Well, that's just a power rule thing. So I can rewrite that in its antiderivative form like this. So I've got my negative sign in the numerator to the negative 1 power, because when I add positive 1 to the negative 2 exponent, I get negative 1. And then I divide by the new exponent. Okay, got a lot of negatives there. Plus my constant. I can rewrite that like this. The two negatives cancel each other, and I've just got this. And then I go back and remember, okay, well, what was u? It was cosine x. So I've got cosine x to the negative 1 power plus a constant, and I could rewrite it like this. If I took the derivative of that last thing that we ended up with and used a little bit of algebra, I could end up with what we started with in the integral. Yeah, a little more tricky. Let's look at C. Can I do the same kind of thing with C as I did with B? Because that looks like a chain rule kind of thing to me. And the answer is no. What's missing? The derivative of t squared plus 1 would have to have a 2t. And I don't have that. In B, I had the sign there. All I had to do was just put a negative sign in front of it. Here, I don't have 2t to mess with. Okay, so now what? Well, let's multiply all that out. So I FOIL it, and I'm getting this. So I've got 3 separate parts in there that I can split apart because they're being added, and that's what I'm going to do. So I'll rewrite it like this just to make it a little more clear. And remember, on this last term out here, that's really a 1 there. Don't forget that part. So let's keep going. Get the antiderivative, and I'm ending up with this. And that's okay. I don't have any negative exponents. If you wanted to, you could rewrite it like this. Your choice. Definitely a little more tricky. So we've been looking at problems that we are getting the indefinite integral for as a solution. In other words, we've got that constant of integration in each one of our answers. This one changes up a little bit. This one wants us to find that general solution, like we've been doing, but also the particular solution that makes f of 1 equal to 3. F here being the original function, not f prime of 1. All right, so the first thing I want to do is write down my function, and then I'm going to find the antiderivative of that. So I'll rewrite it to help me with the power rule. I add 1 to the exponent. I divide by the new exponent. I'm getting that. And so finally I'm just going to write it like this so I don't have any negative exponents anywhere. So what does that represent? Well, that represents my original function, f of x. So I could rewrite that and say, well, all right, f of x equals negative 1 over x plus c. Now that's our general solution. Remember, there's a zillion and a half functions that have a derivative of 1 over x squared. That c reminds us of that. But they want us to also find the particular solution. So we take that, and they're telling us f of 1 equals 3, which implies, when I stick a 1 in there, negative 1 over 1 plus c equals 3. I'm just plugging a 1 in, which tells me this, which tells me that for that particular solution, c is 4. So I can rewrite my function in a particular situation as this. And that matches the parameters of the question here. All right, read this question. We're throwing a ball straight up. Initial velocity of 64 feet per second. We're standing on something that we're launching it from 80 feet up. They want us to find the position function and also how long is it going to take for the ball to hit the ground. Now out here at the end, that little a of t stands for the acceleration based on time is a negative 32. So keep in mind a couple of things. First of all, acceleration is what we get when we take the velocity and find its derivative. So acceleration is velocity prime, if you will. And you got to remember velocity, on the other hand, is position prime. So they want us to find the position function. And so here's my drawing. We're launching it 80 feet up. It's going to go straight up and come straight down. We're sending it up at 64 feet per second. Okay. Then we have to remember, here's the general form of a position function. We've got some kind of acceleration plus some initial velocity plus some initial height. Okay, now then, acceleration and velocity are functions of time. The initial height doesn't change no matter what the time. So we're going to have time involved in the first two terms there. So what I'm going to do is take that and find the derivative for it. Now they told us negative 32 as a function of some time t was the acceleration. The velocity is also a function of time, and that's going to be just a constant there, because you'll see in just a second what happens. So I'm going to find the derivative, the antiderivative of that. So those are added together. So I can rewrite that as this. In other words, split them apart. I can pull the negative 32 out. I can pull the 64 out. Then I'm going to use the power rule. So I take that and I clean it up a little bit. I'm going to divide that negative 32 by 2. And so I'm getting this. That is our general position function as it relates to time. Okay. Part 2 of what they want us to find. I'm going to put the 80 in there, because remember that C in the general solution stands for, well, how high are you when you launch that ball into the air? So I'm plugging the 80 in here, and this makes it now a particular situation. All right, so here's our particular function. Now then they're asking us, how long will it take for the ball to hit the ground? Well, what's the position when that occurs? 0. It's lying on the ground. It has no height above the ground at all. So I'm going to solve for t. I'm looking at that, and I notice everything will divide by -16. So that's my next step. That makes life a bit easier. I factor that. And I get these two factors. I set them each to 0, and one of my solutions is 5, and one of them is -1. Well, now, since this is a real-world problem, t being -1 doesn't make any sense. That's even before I threw the ball. Interesting concept, but not for this problem. So I'm going to cancel that one out. And so I've got my answer there. The ball's going to hit the ground after 5 seconds. When we looked at this position function idea before, we were getting the derivative of it to find two things, velocity and acceleration. Now we're working at it backwards. That's what Chapter 4 is about. Antiderivatives, where we start with a derivative and find its antiderivative. And you've just seen a few examples. It gets more fun.